Okay, up to now, we have done fixed wings and jet planes, comparing them to past years and current year. That was when we did number 1 and number 2. Those were the fixed wings. We did the whole hypothesis test. Should be in your notes. We're going to jump to number 5. We also did jets. Number 5 is comparing gender. It starts out with saying everybody knows that boys are better at folding and flying paper airplanes than girls, especially more complicated ones. We could divide it up into fixed wings alone and then jets. And if you look at the solution in the following pages, I believe that's what the author did. But I'm going to put all the boy data together. I'm just going to put all the boy data together. That means every boy has 2 sets of data, one for fixed wing and one for jets. And so you will go down the list and get all the boys in one list. Okay? All the girls will go in list 2. So you put your data in, I'm going to put my data in, and we'll come back in a second. Okay, I'm going to show you my results. If you have to pause to still keep putting in your data, feel free. So you can see that I have shown a picture of both lists. That's the necessary X bar for boys, 11.365. So let me record that. X bar of boys. $11.365, and then X bar of girls. X bar of girls is 8.1666. Okay, so the question was, comment on this belief that boys are better than girls. Well, apparently the boys are flying their planes farther just based on average. But this could just be sampling variability. And the next set could have reversed the leader of the pack. So what we have to do in number 6, assume this is a random sample of, he just did jet flyers, okay? We did everybody. So it'd be interesting just to pull out the jet flyers and do that. But you can look at the author's solutions when he talks about the calculator. On the next page, he will talk about what he did for number 6. We're going to do both, okay? So I'm just going to X off jet and just say folders and flyers of both planes. That's what I'm going to do in this problem. And decide whether there is enough evidence that the boys are better at flying, folding and flying than girl. Again, we're going to show our steps, and then we're going to interpret he wants me to do a 95% confidence interval. So again, the test is this is actually 2 samples. 2 sample t-test. And if you look at the data again for both, the boys, there's 20 pieces of data. And it's 20. You see that at the bottom there? The girls, there's only 18. So this is one thing you need to realize, that when you are comparing 2 sets of data, it does not have to be the same number in each sample. So the given, I can make this small and move it out of the way if I don't need it. The given is going to be obviously the X bar of girls and boys. And N was 20 of that one. This was N of the boys. I'm going to have to get the standard deviation of the boys. Well, it's in the same one variable statistics. Standard deviation, S of X, 4.3156. 4.3156. And then I'm going to do the girls. So I'm going to do X bar of the girls was 8.1666. N was 18. Standard deviation of the girls is, don't have it memorized, 3.6964. 3.6964. 3.6964. Is that what I said? I already forgot. 6964. Yep. Probably going dizzy as I go zooming in. But now the parameter of interest. If there's no difference in boys versus girls, then mu would be mu of the boys minus mu of the girls. That would be the parameter. Okay? The next thing, and I got to write that out. Let's see. I'll write it out. The true average difference between boys' distances and girls' distances of paper planes. I should say mu. I could just say mu boys minus mu girls is the true difference. Conditions. He already said assume the classes are SRS. So SRS, we're going to take it because he said use it. So now I need to address the situation of shape. Just shape. Yeah, if I look at outliers, I always tend to look at outliers, but do I really need to be concerned with outliers if the sample sizes are bigger than 15 and less than 30? Not so much. The outlier is not a deal breaker. So I'll make a note of it, but I want to look at the shape of boys and of the girls. Data. Okay? So I'm going to let you do your histograms of both the list 1 and list 2, and I'll get right back with you. Okay, if you didn't get enough time to do your histogram, you can always pause right now and finish doing it. But I'm going to show you what they look like. Okay, looking at both histograms, the left one is the boys or the girl. They both look fairly symmetrical. Granted, there's a data value in the left of the boys. There's a couple data values you can see right here and right here that aren't in the girl, but that's just a couple. So that's the boys. And the girls, other than this gap, some might call them both slightly skewed to the right, but it's okay. I'm going to go with both are fairly normal. So if I'm going to check for outliers, I would check the modified box plots. So give me a second. You go ahead and you change your graphs to box plots, and we'll take a look at those. Okay, you can see the boys' box plot on the left and the girls' box plot on the right. Sure enough, there are no outliers. Even if there was for more than 15, less than 30, unless it created a very strong skewness, very strong, then you'd have to worry about. So anyway, there's none. So I'm going to write none here. Just, I checked them. Not that I really had to, but the readers, it's all good stuff. So next thing I'm going to probably do is I'm going to get rid of my pictures that I don't need anymore because they're in my way. But nonetheless. All right. Oh, so was that data of the original. So I'm going to put that up there. Okay. Guess I should have moved that over here. That was that. All right. Now that I feel pretty good about the conditions, I'm going to go and talk about the hypotheses. Now, as the person wrote, the author, said that we all know boys are better, but your null hypothesis will always assume that your two different population means are the same. So we say it's equal to 0. And that would mean there is no statistical difference between boys and girls in flying paper planes. The alternative is what the teacher was wanting us to believe is true, is that no, boys are better. Therefore, mu of boys minus mu of girls would be a positive number, greater. And I will say boys fly planes farther than girls. Appropriate statistic? It's a T. And the degrees of freedom, if you're using your chart, if you're doing it by hand using a table, you take the two lists. Which one is smaller? 18. That was the girls. Take one away at 17. Degrees of freedom is 17. You're going to see that the calculator, though, comes up with this very sophisticated formula. But by hand, your formula would be x bar of boys minus x bar of girls, technically minus mu of boy minus mu of girl. But remember, our null hypothesis said mu boy minus mu girl is 0. So technically you didn't have to write this because this is actually goes 0. So that's why your formula doesn't have it. Over the square root of the variance of the boys, that's s squared of boys, over n of boys, plus the variance of the girls over the number of girls in that set, equals 2. And we have all our numbers up there, so let's see if we can put them in here. Let's see. That was 11.365 minus 8.1656. I thought. I'm going to have to back and look at my calculator. 8166. 8166. 666. 81666 over the variance, the standard deviation of the group boys was 4.3156. So 4.3156 squared over, there was 20 sets in the boys, and there was 18 in the girls, and their standard deviation was 3.6964. 3.6964 equals to some value. And then when I get done, I'm going to have to calculate the probability. We'll change it to black. The probability that t, since we're looking for greater, was greater than that value is. So let's use the calculator. I'm not going to key in all those numbers. I'm going to go right to the calculator and do a stat test and do a 2-sample t-test. So I'll be right back. So you should be doing stat test number 4. You want to choose, we have our data in the calculator, so choose data. You can choose stats and type it in. And then you want to choose to have that, the greater than, the test that's greater than. So I have it conveniently here. Here's my data. And you'll notice I did choose mu is greater than mu2. And I did choose, well, I have stats because it's keyed in, but you could have hit data because it was already in. And I get a t-score of a 1.9438. Also look at the degrees of freedom it actually used, 36. And there's the p-value, 0.2988. So let's record this information here. The t-score, as I said, was 1.9438. And then I'm going to say, the probability that t is bigger than 1.9438 is equal to 0.0298. And like I tend to always forget to do, oh, come on, it's connected to it, that's weird. You type that in, write that in again. Forgot to record alpha up there. So it's a good habit to put it up in here in the given. So wherever my givens were, there, alpha 0.05. And so down here, conclusion regarding H naught, I have to reject H naught because because 0.0298 is less than alpha, which is 0.05. And because I rejected alpha, there is statistical evidence that boys do fold and fly paper planes better than girls. Sorry, I'm not, it's just the facts. That's how it came out. And 3%, less than 3% chance of it happening randomly, this data set occurring, is not supposed to happen. It's not, it's a very low probability of happening. So therefore, we say that our data justified that belief. Now, confidence interval, I'm going to go and just change my stat test to the t interval, and I will put it right here in just a second. So I'll be right back. Okay, as I was doing my confidence interval, I realized that I forgot to do something. Look at your option on the t-test. You have an option to, let's see, did this say pool or not pool? No, it didn't. I'm okay with that, I guess. My confidence interval, let me get my confidence interval piece out of there. Does this change anything? No. Okay. So I was looking at some stuff. But you had an option to pool or not pool. This little button right here. You want to not pool because you can't guarantee that your samples came from the same, that the boys and girls each had the same standard deviation. So you don't pool. So make sure you select don't pool. And there's your lower and upper. So I'm going to go 0.0886 in 5.1853. So here I go. I'm going to write the answer out first while I'm here. 0.0866 all the way to 886. 51853. 5.1853. 5.1853 is where the distance should be. And the thing about it, since 0 is not in that interval, again, that's sort of more evidence that boys and girls are not equal in this sample. So 0's not in there. It's on the left, okay? By the way, the formula was is X bar, always using the samples, X bar of boys minus X bar of girls, plus or minus your T star by hand, degrees of freedom still would have been 17, times the square root of the variance of the boys over n boys plus the variance of the girls over n girls. And plugging, plugging in all the data. I don't have to really plug in the data and show it because we already did up here. You don't have to do it twice. You can use your calculator answer. And what does that mean? I am 95% confident that the true mean difference of paper plane flights between boys and girls is between 0.08 feet and 5.19 feet. Okay? There could be a mistake somewhere here. Who knows? You can investigate yourself, taking my time. You will notice that is the author's explanation with a calculator of all of problem number 2. That was, we were doing, I believe, fixed wing. Problem 3 was jets. And maybe he was comparing that they were just not the same jets. I'm not really sure what he did. He may not have done the same thing we've done, but I think he may have made a mistake in his interpretation of number 3 than what we read. I will maintain that we were right and he's wrong. But it's still a good problem if you want to look at it that way. He talks about number 4, whether students fly sleek jets farther than wing. That's all here. There's a 6 that we just did. I think he just did jets, though. He just did jets. We did both. I'm curious if he did just the jets, what was his conclusion? 2-sample t-test. Looking for his, that's his data. Looking for his p-value. Even smaller p-value. There was not enough evidence to reject the null hypothesis, that there is no evidence that the boys throw farther than girls. So he rejects it, rejected H naught as well. And that takes us to your packet of problems that you have. Number 1 was already one of your homework problems. Just a 1-sample t-test. Number 2 was a 1-sample t-test with the data that you had to key in. So you should have those down already. When you get to number 3, this was a large Vegas casino advertised as slot machines in the area, and the casino averaged 95% payback. And as first of 15 slot machines were used to see if the average play was different than 95%. Perform a hypothesis test at the 2% level. The alphas changed to 2% and generated 98% considered for the average payback of slot. That's just a very simple one sample t-test. Nothing exciting. Number 3. The Macintosh Sierra operating system is advertised to be faster than the PC Windows version. No one uses Sierra. It's been a long time. But people still argue that the Macintosh or the Apple operating systems are still faster than any of the Windows. Now, they tested 12 random tasks. They timed them. Was there evidence at the 5% level, that's alpha is 5, that Sierra is faster than Windows? Also find a confidence interval. A two-sample t-test. Two-sample t-test. Number 5, they gave you all the data. They gave you the averages. They gave you the standard deviations. They gave you the sample size. Again, that's just another two-sample t-test to find out which whitener is better. Your null hypothesis should still be that mu all white minus mu bright smile would equal to 0. So that one has no difference from what we've been doing. Number 6 was just checking scores using a graphing calculator on an assessment or a quiz, and another group of kids or students did not use a calculator, graphing calculator. And notice the sample sizes are not the same, so we know it's just a two-sample t-test. Okay, I jumped all the way to number 10 because this problem is a little different than the other 9. The other 9 was either a one-sample t-test or a two-sample t-test. Number 10 is it looks like there's 2 samples, but really we're going to treat it as one sample in a few minutes because it's called a matched pair. If you read this problem, they thought that listening to the sound of the surf would help people get to sleep. So they picked an experiment. Now, experiment by default is a randomized assignment of treatment. So it's not an SRS, but we'll say it's a randomized experiment. Some nights the sound of surf was piped into their bedroom, and other nights no sound was used. The experiment was run for a period of time, and the average time it took to fall asleep was monitored and averaged. Following is the data for the 10 people. Perform hypothesis tests to see if the possible effectiveness of the sound of the surf for sleep, and then construct a 95% confidence interval. So this is, when you look at this data, this is actually person 1. They have 2 different times. Their average time that they fell asleep with surf noises. And look at here, this person 1 took longer without the noises. Look at person number 2, same thing. Took longer without the surf noises. Person 3, it was close. Very close. It was a tied. Didn't matter for person 3. Person 4 took less time without the noises. So, it's kind of like we don't know what is the truth. So this is called a matched pair. Matched pair. Because we're matching these 2 together with one person. There's a reason that they are not independent populations of data. They're not independent because they were both from the same person. So there's an overlap of what could be causing a person to sleep. You don't know what makes a person fall asleep. Other issues could have been going on. You don't know. So you haven't excluded any other variables of the sleepers. So what we do with this, we put both lists in, list 1 and list 2. What we're going to do in our calculator, under list 3, we're going to take list 1 minus list 2 and make a third list. That's the list that we will do one variable statistics. That's the list that we will do a one sample t-test. Even though it's two sets of data, we merge it into one. Okay, so take a few minutes, get the data in, and I will get back with you. Okay, so I have all my data in list 1 and list 2. And then I did a list 3 being L1 minus list 2, which is why you have that first term as a negative 1.2, which meant it took longer for that first person to fall asleep without the surf sounds, because that meant the second list was greater. The third one was a 0 because they tied. And so all the negatives will imply falling to sleep better with the surf sounds. Positive numbers in that list 3 would be it was better not to have noise at all. I went and ran the one variable statistics for my new list 3. So I'm going to record those as my given. I don't really care about the separate list, I just care about list 3. Okay. Get this out of my way. Oh, it did that to me again. Connected that to the picture. Weird. What I had done was I've already listed that this is a 2-sample match pair t-test. I've given my X bar of surf sounds minus no surf sounds was a negative 1.16. And the standard deviation of surf sounds minus no surf sounds was a 1.2375. N is 10 and alpha is 0.05. Now, you have to have the same number in each sample in order for it to be a matched pair. You will get an error, obviously. You'll make a mistake if your lists do not have the same number in each. So I'll just double check my calculations there. The calculator, there's a negative 1.16. There's my S of X, which was 1.2375. There's my N is 10. So I feel confident that we have the right values there. Moving on here. Parameter of interest. It's not mu1 minus mu2 or mu sounds minus mu. It's just one mu. It's just one mu. And I'm just going to call it mu of surf sounds minus no surf sounds is the true average time it's the true average time of the difference in their time it takes to fall asleep with surf sounds minus no surf sounds. Conditions. It's an experiment. So, I'm going to call it a random allocation of treatment experiment. So my SRS will be taken care of. Sample size is 10. I'm concerned. N is less than 15. I need to look at the data. I need to look at the scatter plot, the histogram and the box plot modified. So let's create those graphs and we'll come back and view it. So take a few seconds. Pause it now if you want to till you get it done, because I'm going to go do mine right now. Okay, I've put both pictures on the screen here. One is the histogram, which wasn't very exciting, but it doesn't look, it's not skewed, so it's normal. Actually, it's not normal. I'm going to say it is uniform. Uniform. And if I look at the modified box plot, there's no outliers. No outliers. So that's good to go. I'm all ready to work this problem out. Move that out of the way. Oh, I guess stuck to it, so I'll just rewrite it again. No outliers. Oh, one pen. So now I'm just looking at my null hypothesis, H naught. Mu with surf sounds minus no surf sounds. If the surf sounds made no difference, we would expect 0. Let's double check what we're actually looking for. We want to find evidence. Let's see, perform the hypothesis to determine the possible effectiveness of the sound of the surf. So if the surf does help, then I'm expecting a negative number. It took longer to fall asleep with no surf sounds. So that would mean HA, mu of surf minus no surf, would be less than 0. And how would I word it here? I would write true difference in falling asleep with surf sounds, or none, is 0. That means surf sounds don't help. But I suspect it does. So I'm saying true difference in falling asleep shows surf sounds helps fall asleep faster. Appropriate statistic, it's just a one sample t-test with degrees of freedom of 9. So t, degrees of freedom is 9, will be equal to x bar of surf minus no surf minus mu of surf minus no surf over the square root of standard deviation squared, that's the variance of surf minus no surf, over n, will be equal to some number. Let's see, let me put my values. I do have the values. X bar was negative 1.16, negative 1.16, minus the 0, over the square root. Standard deviation was, if I have it right, was 1.2375. 1.2375 squared over 10. That's really easy to key in by yourself. This one would be very appropriate without a calculator. You can use a calculator, but you don't have to use the statistical feature to find the p-value, because it looks clearly there. Easy. It's easy to do. But I'm still going to use the calculator. And I'm still going to find out the probability that t is less than that number, because I am going to the left. I want to find out the probability that you would be that small. Okay? So pause the video now, calculate it, see if you're right. Beat me to it. Okay, my data is there, and if I look at what the calculator gave me for the t-score, I think I have it right. I used stats, and I'm choosing the left tail. I got a t of a negative 2.96, negative 2.96, and a 0.0079. So that's negative 2.96, and the p-value being 0.0079. Negative 2.96. All right, I think I don't need these pictures anymore. Move them out of the way. And what do I have here? Oh, why do all these pictures keep coming back? I lost my negative. It lost it. Negative 2.96. And wow, that is small. It's not even 1%. Since the p-value equals 0.0079, which is a lot less than alpha, which was 0.05, I reject H naught. That means there is strong evidence that, remember what H alternative was? That mu of the, well, let me not write it as that. We just write the true difference in falling asleep time is less than 0. Which does that mean? This is a very important part right here. Surf sounds do help. That's important. Now the interval, I think I had that up here. Where did I put it? None of those. Let me look. I have the interval here somewhere. Well, it's weird. I can pull that one up. Oh, there it is. Make sure this is the right one. Yeah, the X bar negative 1.16. And it's 10, 95% confidence level goes from a negative 2.0452 negative 2.5472 all the way to 0.2747. Interesting. So the formula would have been X bar of surf sounds minus no surf sounds plus or minus T star with the degrees of freedom equals to 9, and we were obviously having to find the T at a 95% confidence times the square root of S squared of surf minus no surf over 10 is that interval. I am 95% confident that the true difference falling asleep from surf sounds versus none is between negative 2.5 minutes, which negative meant you're falling asleep better with the surf sounds, to 0.28 seconds. Minutes, not seconds. The interesting thing here is 0 is in the middle. 0 would have been here. But it's so on the right side that most of your data is on the negative side. So there's always that chance that it isn't really helping, but we're going to run with it. Okay. Your job is to finish all those problems in your packet. And there will be an evaluation based on you watching this video. Okay? Over and out.